Hello everyone, my name is Inga Kresic, I'm a PhD student. The topic of my paper is the influence of different seed positions on mechanical properties of stochastic structures with semi-controlled nodes. Cellular structures are part of additively manufactured components because of their excellent properties. In nature, they can be seen as honeycomb, foam, bone, and wood, showing the porosity and smaller volume fraction of solid matter. These structures are divided into stochastic and non-stochastic lattice structures depending on the arrangement of their unit cells, periodic or random, as shown in figure. They are widely used in biomedicine, aerospace, automotive, energy observation, and sports equipment design. Stochastic structures consist of non-periodic cells that form structures of interconnected struts. They imitate foams but don't behave like them. Their geometry is achieved by defining the parameters such as nodal connectivity, strut density, and strut thickness, as shown in figure below. Nodal connectivity is the number of struts connected to a node. There are errors in the nodes of the generated stochastic structures that prevent the implementation of numerical analysis. Therefore, this paper aims to present an algorithm for generating stochastic structures with semi-controlled nodes focusing on the distribution of seed points using the Voronoi tessellation method. So far, the authors mainly use metallic printed stochastic structures. In their research, the production parameters of samples produced by powered bed fusion affect their mechanical properties. It proposed a modified isotropic stochastic structure that has equal stiffness in all directions, overcoming the limitations of the powered bed fusion method with the aim of application for small components in the field of biomedicine. Zaninetti presented a Voronoi tessellation algorithm with a random distribution of seed points. Alkner et al. Presented generated structures of equal cylindrical volume, chaining the geometry of the usual Voronoi structure using longitudinally elongated Voronoi struts in the z direction. Newly generated structures may exhibit improvements in mechanical properties. The next slide is Voronoi tessellation. It enables the design of structures with a regular cell geometry and variable cross-section of struts using random points. This method divides a given volume into Voronoi cells, as shown in the figure below. The 5 random points is equal to 5 Voronoi cells. The size and shape of cells depend on the number and position of seed points. Stochastic structures are generated in the software running CR7 with the parametric design plugin Grasshopper. It's necessary to define the distribution of points using component populate within certain boundaries. Component cool duplicate is used for nodes by defining close points within defined tolerance. The strut radius is added to the model to obtain stochastic structure using the multi-pipe component. The radius is the same in all struts using node size, as shown in figure below. Porosity affects the mechanical properties of stochastic structures. Structures with high porosity are weaker because the distance between the Voronoi cells is greater, while those with low porosity are much stronger. The next slide is numerical analysis. Stochastic structures were generated in the box volume of 30 mm by varying the distribution of an equal number of pseudo-randomly points. The compression of 10% deformation was performed in ANSI software to obtain von Mises stress and the required force. The results are shown in the figures. The highest force can achieve the structure with 12 randomly points of 97 Newton, followed by the structure with 10 points of 91 Newton. The structure with 11 and 14 points are equal of 85 Newton, and structure with 13 points can achieve force of 82 Newton. Each structure differs in the distribution of seed points for the same input data. The structure that can withstand a more significant force depends on the number of points and distribution of points in a given volume. Stochastic structure with semi-controlled nodes were generated in the software NCR7 Grasshopper using the Voronoi tessellation method, which divides a given volume into Voronoi cells. The structure was tested in ANSI software to obtain Fermi stresses and required forces. The results differ for the same seed number in the same volume, but for different seed positions. It can be concluded that the distribution of pseudo-randomly points strongly influences the generation of stochastic structures. For this reason, the law of point distribution specific volume should be found to improve mechanical properties. Thank you for listening.